Hello, Joe, can you hear me now?
Yes.
Yes, I can hear you.
Okay, thank you. Hmm. Yo, so, uh, let me host the meeting, then Joe, okay? Hello, everyone. Now it's time to open our Savnet meeting. So it's a pity that I and Joe cannot attend the meeting on site. So we ask the Howie to help us to uh, uh, assist this meeting. So here is the noteware. Sorry. So it just want to emphasize uh, the policy. So it just want to emphasize the patent and the code of conduct. And such a main point is by participating in IETF, you agree to follow the IETF process and the policies. And if you are aware that any IETF contribution it is covered by patent and patent application, you should disclose it during the working group or adoption call. And as a participant, you should aware that your written audio and video will be published, used by the and the code of meeting will be made public. Uh, and also your personal information that you provide to the ITF will be handled in accordance with the ITF privacy statement. So for more information, you can read in the relevant document cell below. And here is our working group status. Currently, we have 3 working documents: the proper document and the intra-domain architecture document. And there are many more documents for now for the other issues. For example, the inter-domain document and the intra-domain solution, and some general solution component. And for the solutions, we have the several directions: IGP based, BGP based, and the newly provided controller based solutions. We will discuss them in these meetings. And we also have some document for the management proposal. So the goal of this meeting, we will focus mainly for the introduction and discuss of the update architecture document for the inter-domain. And after that, we will discuss some general survey table and some current survey measurement and benchmarking measurement for survey. After that, we will discuss the various solutions for intra and inter-domain survey mechanism. Here is the general agenda. So I have updated last day for presentation. The first part is the architecture and the general topic, and the second part is about the solutions. So that's all for our meeting. Hey, Joe, do you have other missing for the meeting? So if you have no comment, then we will start the first presentation.
Okay. Can you hear me, Adrian? Hi. Good morning. Can you hear me?
Good morning. We can hear you.
Okay. Let's get started. Good morning, everyone. I'm Li Bin Liu from Zhongguancun Lab. I will present the inter-domain source address validation Savnet architecture. Next slide, please.
Hello, Aijun, if you're okay.
Okay. Okay. The inter-domain Savnet architecture aims to provide a comprehensive framework for developing new inter-domain solve mechanisms. Here is a summary of the historical versions. We have 10 versions in total. During the Savnet workgroup meetings from Ietf 115 to 119, we have presented the draft updates from version 00 to 07. After Ietf 119, we have updated two versions according to the comments and the feedback from the Ietf 119 meeting, as well as the discussions in the mailing list. Now I will present the version 09. Sorry. Sorry, I cannot control the slides. Okay. Before introducing the updates of the version 09, let's first quickly review the version 07 and the comments. For the version 07, we summarize the incentive of the inter-domain Savnet architecture and introduce the details of the inter-domain Savnet architecture, including the overview figure, the sub-specific and general information and their differences, and the sub rule generation based on various sub information sources. We also describe the Savnet communication mechanisms, including the sub-specific, general, and management information communication mechanisms. We also illustrated the use cases of the inter-domain Savnet architecture. Here, sorry. Here is a summary of the comments on version 07. We have characterized the comments into different types. The first type is the comments on the details for acquisition of sub-specific information. Avro asked that how the source AS obtains its own sub-specific information. And he also commented that for this document, we need to recognize for some cases, inter-domain Savnet may not work as expected until a wide deployment is achieved. And he also asked that how the source AS is aware of the failures and updates the sub-specific messages. And the second type is the comments on using RPKI, ROE, and ASPA objects as a sub-information source. Ben commented that if SAL using RPKI is deployed, it will jeopardize the use of RPKI in routing security. The third type is the comments on priority-based scheme for using SAL information sources. All have commented that this scheme may not generate accurate SAL rules when the high-priority SAL information sources are lacking and the information from low-priority sources is not accurate. Both Q and Ben also asked whether the draft considers the security issues. Repeat the response again. The document does how the security considerations on version 07. And I will also have some minor comments on the draft writing. We have revised it accordingly. Here are the responses to the comments or response 1. In section 7.1, we have revised the content to illustrate the process for acquisition of such specific information and further clarify the specific scenarios for wired deployment of Savnet agent. In details, we have updated the figure 9, which shows a detailed example to explain how the source AS obtains its self-specific information and communicates it to the validation AS. And we have added a new paragraph to illustrate the scenarios explicitly, where static route and network failures exist. We have discussed the updates of section 7.1 and record comments in the Savnet mailing list. Our response 2, in section 6, we have described the requirements for obtaining accurate source information from the low priority information sources and avoiding the jeopardizing the user RPKI. We have discussed the requirements for guaranteeing the accuracy of low priority source information sources and avoiding the jeopardizing the user RPKI in the mailing list. For the response 3, we have added a new section to illustrate how Intra-domain Savnet meets the requirements proposed in the Intra-domain Savnet problem statement draft. We have discussed the overall updates of the whole architecture draft and the record comments in the mailing list as well. Here is a summary of the main updates compared to version 07. We have revised the source information-based section by adding a new paragraph to further explain the recommendations for different source information sources. We have revised the Savnet communication mechanism section. We have updated the figure 8 to show that Savnet agent obtains different source-related information from different sources. We have updated figure 9 and its corresponding descriptions to explain how the source AS obtains the source-specific information, and added a new paragraph to illustrate the deployment scenarios where static route and network failures exist. We have also added meeting the design requirements of the Intra-domain Savnet section. All these updates have been discussed and illustrated in the Savnet mailing list. Before introducing the main updates, let's review the Intra-domain Savnet architecture figure. The architecture figure displays an AS level topology and the communication flow of the source-related information between AS. Here we use ASX as a representative to describe the topology and illustrate that what source-related information the Savnet agent will collect and where the information is from. The topology displaying all PRAS or ASX, including customers, little peers, and providers, and the existence of multiple physical links between AS. Arrows in the figure indicate the direction of the corresponding source-related information from its source to ASX. And ASX has deployed Savnet agent and can communicate the source-specific information with its customer AS, which also deploys the Savnet agent. And the local routing information from BGP messages and the RPKI, RO, and ASPA objects from local RPKI cache server and the IR data from the IR database. Okay, let's look at the main updates of the source information-based section. In this section, we discussed that generating source rules based on the priorities of source information sources. We have updated that the priorities of the source information sources are recommended rather than mandated. The operators can specify the priorities of source information sources by themselves. And when the source-specific information is not available, a new source mechanism can use the low-priority information source and should ensure the correct information is obtained and adopts appropriate cell actions on the data plane. Besides, when using the RPKI objects as the cell information source, the new inter-domain cell mechanism should avoid jeopardizing the use of RPKI in routing security. Then let's go through the main updates of the Savnet communication mechanism section. In this section, we have modified the name of the mechanism for communicating management information from management mechanism to management information communication mechanism. Then let's look at the updates of the self-specific information communication mechanism section. In section 7.1, we have used an example to display the detailed process about how the Savnet agent of the source AS obtains its own self-specific information. As shown by the figures A and B, there are 4 AS. S1 and S4 have deployed the Savnet agent. Thus, they can communicate the self-specific information with each other. Figure A shows that S4 advertises its prefix P4 to S1 along the path S4, S2, and S1, and the path S4, S3, and S1. S1 selects the path S1, S2, and S4 as the best path for the legitimate traffic, with source addresses in P1 or P6 and the destination addresses in P4. So S1 knows that its legitimate traffic will enter AS4 from the direction of S2, which is a specific information. So AS1 can communicate it to S4 via the subspecific messages. We have further supplemented the descriptions for the scenarios of static route and network failures in section 7.1. For the scenarios of static route, in some cases, operators may override the default BGP decision by using static route. For these cases, the wide deployment Savnet agent is required. For the scenarios of network failures, the preferred AS path or source AS may change due to network failures. The Savnet agent should be aware of the network failures by detecting the route changes and launch self-specific messages to update the self-specific information in a timely manner. And a wide deployment of the Savnet agent can make the network failure sensing more sensitive. Okay, let's look at the updates on meeting the design requirements of inter-domain Savnet section. Inter-domain Savnet architecture proposes the guidelines for the design of new inter-domain cell mechanism to meet the requirements proposed in the inter-domain Savnet problem statement. For the first requirement, improving validation accuracy over existing scenarios, cell-specific information can generate more accurate cell rules than the general information. For the second requirement, working in incremental and partial deployment, Savnet agent can be deployed incrementally, and when the cell-specific information is not available, general information can be used to generate cell rules. For the third requirement, reducing operational overhead, the Savnet agent can collect cell-specific information through the cell-specific information communication mechanism and generate cell rules automatically. For the fourth requirement, guaranteeing convergence, a Savnet agent should launch a cell-specific message to adapt to the route changes in a timely manner. And for the last requirement, providing necessary security guarantee, existing security mechanisms can be used and a new security mechanism can be designed. And in sum, the inter-domain Savnet architecture and its updates have been presented during the meetings from Ietf 115 to Ietf 119. And this document addresses all the comments from our community and is discussed in the mailing list of Savnet work group. And the new inter-domain cell solutions developed following this architecture can meet the requirements proposed in the inter-domain Savnet problem statement draft. Thank you very much for the all the comments and feedback from our community to help improve this draft. And I think it's a time to go to the next stage. We request work group adoption for this draft. Thank you very much. I'm happy to take your questions.
Hello, Libin, can you hear me now?
Yes, I
Yeah.
can hear you.
Okay, here I want to ask one thing. Currently there are some other person propose a controller-based solution for the inter-domain. So would you like consider such solution within your architectures?
Yeah, I know that. I think I think this is not conflict with the current version of the inter-domain architecture draft is not conflict with the controller version because the Savnet agent can be deployed at the export router. Maybe can if the deployed network can support controllers, the Savnet agent can be deployed at the controller, I think.
Okay, but now as I remember, there is no mention of the controller within your architecture. So I think you should supply some sentence to add such component or add such possibility to use the controller as additional component to fulfill our aims. Okay.
Okay, sure. Thank you.
So yeah, here I want to remind the other person for the presentation, your allotted time will include the question time. So I think you should leave more time for the discussion. Okay. So if there is no other person ask questions, we can change to the next slide, next presentation.
Okay. Okay, let's go to another draft, benchmarking methodology for source address validation. I will introduce the 6 aspects of the draft. Sorry. Okay, proposing standard benchmarking methodology is important for evaluating the performance of intra-domain and inter-domain sound mechanism fairly. For network operators, the benchmarking methodology can help them get a more accurate idea about the performance of sound devices in their deployed network environments, in order to select the appropriate sound mechanisms. And for the device vendors, the benchmarking methodology can help vendors test the performance of the sound implementations. And the benchmarking methodology can also guide how to evaluate whether the new intra-domain and inter-domain sound mechanism can satisfy the design requirements proposed in the intra-domain and inter-domain Savnet problem statement drafts. There are 2 objectives of the benchmarking methodology, including assessing which sound mechanism perform best over a set of well-defined scenarios, and measuring the contribution of subsystems. For the sound device under test, the benchmark aims to test the performance of individual sound devices, such as hardware or software routers. And the benchmark will showcase the performance of various sound mechanisms for a given sound duty and network scenario. The DOT is connected to other network devices to construct the network topology. since the location where the DOT resides in the network topology affects the cell accuracy. And the tester can be connected to the DOT directly or by other devices. And it can generate traffic to test the cell accuracy, control plane, and data plane performance. And the network traffic generated by the tester should specify the traffic rate, the proportion of spoofing and legitimate traffic, and the distributions of their source addresses. For the DOT and the device configurations, the device in their topology can have various routing configurations, and the generated cell rules of the DOT is also affected by the configurations of the other devices. We have proposed the 6 cell performance indicators in the draft. The proportion of improper blocks refer to the proportion of legitimate traffic, which is blocked improperly by the DOT across all the legitimate traffic. And the proportion of improper permits refer to the proportion of spoofing traffic, which is permitted improperly by the DOT across all the spoofing traffic. Both of them can measure the cell accuracy. The protocol convergence time represents the period during which the cell control plane protocol converges to update the cell rules, and it is the time elapsed from the beginning to the completion of the cell rule update. And the protocol speaking agent processing throughput measures the throughput of processing the packets for communicating cell-related information on the control plane. Both the protocol convergence time and the protocol speaking agent processing throughput can measure the cell control plane performance. The data plane cell table refreshing rate refers to the rate at which a DOT updates its cell table with new cell rules. And the data plane forwarding rate refers to the cell data plane forwarding throughput for processing the data plane traffic. Both of them can measure the cell data plane performance. This document proposes the benchmarking tests in terms of cell accuracy, control plane performance, and the data plane performance. For the cell accuracy of intra-domain and inter-domain cell, the objective is to measure the cell accuracy of the DOT to process legitimate and spoofing traffic in various intra-domain network scenarios, including cell for customer or host network, cell for internet-facing network, and cell for aggregation router-facing network. And in various inter-domain network scenarios, including cell for customer-facing AS and cell for provider or peer-facing AS. We present 2 test cases for the intra-domain sum here. Test case 1 shows the cell for customer or host network in intra-domain symmetric routing scenarios. The DOT is directly connected to the router 1 and the tester. Different from under the legitimate traffic with source addresses in 10/15 and the ones with destination addresses in 10/15 have the same path. Different from this, the test case 2. In the test case 2, the outbound traffic with source addresses in 10/16 and the inbound traffic with destination addresses of 10/16 have different paths to form the intra-domain asymmetric routing scenario. The tester can send the legitimate traffic using 10/15 as source addresses and spoofing traffic using 10.2/15 as source addresses. For the 2 test cases, the expected results is that the DOT can permit the legitimate traffic and block the spoofing traffic from network 1. And we also present the 2 test cases for the inter-domain cell. Test case 1 shows the cell for customer-facing AS in inter-domain symmetrical routing scenario. And the 2 figures show the test setups for the 2 test cases. And the tester is connected to S1 and can send legitimate traffic using P1 as source addresses and P4 as destination addresses, and the spoofing traffic using P5 as source addresses and P4 as destination addresses. For the 2 test cases, Different from test case 1, the test case 2 configures the prefix P1 and the prefix P6 with no export to form the inter-domain asymmetrical routing scenario. And for the two test cases, the expected results is that the DOT can permit the legitimate traffic and block the spoofing traffic from the direction of AS2. For more test cases, you can read the draft. For the control plane performance of intra-domain and inter-domain cell, the objective is to measure the protocol convergence performance and protocol speaking agent performance. Figures A and B shows the test setups respectively. For the protocol convergence performance, the protocol convergence time is calculated by subtracting the beginning time from the completion time of the protocol convergence process. For the protocol speaking agent performance, the protocol speaking agent processing throughput is calculated by dividing the overall size of the protocol messages by the overall processing time. So for the data plane performance of intra-domain and inter-domain cell, the objective is to measure the data plane cell table refreshing performance and the data plane forwarding performance. Similarly, figures A and B shows the test setups. For the data plane cell table refreshing performance, the data plane cell table refreshing rate is calculated by dividing the overall number of the updated cell table entries by the overall cell table refreshing time. And for the data plane forwarding performance, the data plane forwarding rate is calculated by dividing the overall size of the data plane packets by the overall forwarding time without packet drops. For the security considerations, we would like to test the DOT in a lab environment, and the lab network is isolated from the production network to guarantee that the test traffic is not forwarded to the production network. For the next step, we would like to seek feedback and comments, and the collaborations are welcome. Thank you very much.
Hello, Nangong from Huawei Technology. Can you go to page 12 about the control plane performance? Yes.
Yeah.
For in figure 2, is described that advertising protocol messages at the rate of 10%, 20%, and 100% of the link capacity. I'd like to know whether we have so many protocol messages in real networks. You know, maybe 10% of link capacity of control plane protocol messages, maybe a large number of data.
Yes, that's a good question. I think I don't have a very accurate answer because I don't have the survey. I think it is worth starting about that. I think here for this test setup, I want to do the compression testing. So advertise. So we will advertise the protocol messages based on their link capacity with different proportions of the link capacity.
Okay, thanks.
Yeah, Vivian, here I want to ask a question. Either any vendor has the device from any vendor has been tested under these schemas or benchmark method?
Yeah, actually, we do some tests by ourselves, because we have the current state is not known. We will welcome collaborations with the people from the vendors to push this benchmarking test.
Okay, We would like to see the result later, test result later for the for benchmark test. Okay.
Sure.
Sue, here's Wally. On this
Hi.
one, thank you for the work. Very excited to see this. It's important for the performance. Couple just comments on it. Protocol convergence time performance in the benchmark working group for either BGP or data has some long history about how you measure when protocol convergence starts. You might look at that. Second, data streams usually matter in this time. Data streams of attack traffic or data streams of data. Again, you'll see that in the benchmarking working group. We can talk offline other than that. Thank you.
Thank you.
Okay. If there are no other questions, we will turn the next presentation. Thank you, Libby.
Thank you very much.
Hello, can you hear me?
Yeah, I will pass the slide control to you.
Thanks.
Okay, you can begin the presentation.
Okay, thank you. Good morning, everyone. I'm Shuai Wang from Zhongguanxun Lab. Try to control slides. Today, I'm going to share some new advances in our self-deployment measurement, which is about how to identify the presence of outbound source address validation remotely. Traditional methods of detecting OSAL deployment requires a measurement client in the tested network, but this is time-consuming and not scalable. So there is a need for a remote method to identify OSAL deployment. So first, let's start with how pre-work has remotely identified the absence of OSAL. For a given network to be tested, we should first find a transparent forwarder in the tested network. A transparent forwarder is a device that does not modify the source IP address when forwarding data packets, but modifies the destination IP address. Next, we send a packet from the scanner to the transparent forwarder, with scanner as its source IP address and the transparent forwarder as its destination IP address. We should know that this is a normal packet. Then, when the transparent forwarder receives a packet, it will change its destination to another IP address. This new destination is denoted as forwarding destination, since the transparent forwarder sends a packet whose source IP address does not belong to the transparent forwarder. We regard it as a spoofed packet. Finally, if the destination receives a spoofed packet, it will directly respond to the scanner, because the source IP address of the spoofed packet is the scanner. At last, when the scanner receives a response packet, we will compare the source IP address of the response and the destination IP address of the query. If they are different, we can learn that the spoofed packet is not discarded, and the tested network does not deploy OSAL. However, if OSAL is deployed in the tested network, the spoofed packet will be discarded. Then the forwarding destination cannot receive the spoofed packet. Finally, no response will be received by the scanner. It looks like that we have found a method to identify the presence of OSAL by observing no response as the scanner. Unfortunately, it does not work in practice because we do not know in advance which IP address is used by a transparent forwarder. So if the original packet is not sent to a transparent forwarder, the forwarding destination will also receive no spoofed packets. In this case, no response will be received by the scanner. So how to distinguish the reason why the scanner does not receive any response from the forwarding destination? To this end, we propose OSAL route. OSAL route uses traceroute to track the path of a data packet and can know whether a spoofed packet is generated. OSAL route sends packets with increasing time to live or TTL. When a packet with TTL 1 reaches the router R1, an SMP error message will be sent back to the scanner. Because the source IP address of the SMP error message is R1, we can know the first hop is R1. Similarly, we can know that the second hop is transparent forwarder and the third hop is R3. Then the spoofed packet is discarded by OSAL as a false hop. As a result, we will receive no SMP responses from the false hop. The figure in the upper right corner shows the response packet. We can see that the source address in the IP header tells us about the node in the path, and the destination address in the SMP payload tells us about the destination of a probing packet that triggers TTL exceeded. The change of the destination of probing packet tells us that a spoofed packet is generated. OSAL rules use DNS queries and TCP in SIEM packets to locate and interact with transparent forwarders. We have discovered more than 2 million transparent forwarders by enumerating every single routable IPv4 addresses. After removing transparent forwarders that cannot help us in full OSAL deployment, more than 6,000 transparent forwarders fail to send the spoofed packet outside their origin ASs. That is, they are located in networks that deploy OSAL. So which kinds of transparent forwarders cannot help us in full OSAL deployment? It includes we find about 4 cases. First, the forwarding destination is in the same AS as the transparent forwarder. Second, the transparent forwarder may be a router in transit AS. Third, the IP address of a transparent forwarder is unknown. Fourth, the transparent forwarder may be multi-home. And there may be more cases that need to be removed due to the complicated internet. We are working to find more reasons. Our results show that 440 ASs deployed OSAL with 169 ASs is identified by sending TCP SIEM packets. One prefix is also mirrored by KDA spoofer, confirming the presence of OSAL, which aligns with OSAL route. The majority of spoof packets reach their fastest hop at the fourth hop, with only less than 2% transmitted beyond 3 hops. This distribution is consistent with prior work. The measurement results are published on our website and updated monthly. It includes spoofable prefixes, blocked prefixes, and inconsistent prefixes. We are working to contact network operators to inform them of the self-deployment in their networks. A large ISP in China has acknowledged our measurement results for some of their prefixes. Moving forward, we encourage researchers and the network operators to independently validate our measurement results and provide some feedback. We will also report our results to the corresponding network operators, including both the presence of OSAL and the absence of OSAL. We invite the community to participate in OSAL route measurement. Based on the feedback, we will continue to refine OSAL route. If you are interested in collaborating or have suggestions on how we can enhance our measurement framework, please reach out to us. Thanks for your attention, and the comments and feedback are welcome.
Yeah, sure. One question. Can you distinguish the partly deployed OSAV from the fully deployment and non-deployment?
Yes, we think this is inconsistent prefixes. We mean that if a spool packet take a path, and in this path OSAL is deployed, maybe the spooled packet will be discarded, so we can know. But if the spooled packet take a different path and no OSAL in this path, then we think no OSAL in this path, and we think this prefix is inconsistent prefix.
Yeah, but for your probe packet, I think you cannot control the path that they across the entire network.
Yes. So we think this is a best effort measurement.
Okay, thank you.
Thank you.
So Tobias Siebig, Max Planck Institute for Informatics, but in this case, speaking for myself and my LIR in the REP region. So in May 2024, I received an email informing me about ISAF deployment in IPv6 prefix in AS211.286, which apparently was measured either using NAT or an OpenDNS resolver. And curiously, the mentioned prefix at that point in time and any time before that was unrouted. Well, it was routed by the covering prefix, but within the AS itself, it was not being used. So I was wondering how that might reflect on the methodology being used.
Sorry, you received an email to tell you about your network does not deploy ISAL, right?
It told me that it had deployed ISAF and it had used either NAT or an OpenDNS resolver in a prefix in which at that point in time and any time before that, since that AS had been assigned by the RAP NCC, no services or otherwise assigned addresses were.
Yeah. This is we think we send this email. We send this email on behalf of Tsinghua University, and this in this slide we talk about OSAL deployment measurement, and we use Open Resolver to measure ISAL deployment. Yeah. So your question.
There are no hosts in that network.
No host in your network?
Host in that network, which means there is no open resolver which could have been used to measure anything.
Yeah, we think this is a question that we should collaborate to figure it out, because we think our method rely on a host like Open Resolver or something, but you said no host in your network. I think it is weird. So I think we can collaborate to figure it out.
Thank you. I replied to that email in May 2024.
Thanks.
So just follow up on that.
Thanks.
I think we can take the discuss on the list now. Okay, thanks, Trey. We will move to the next presentation.
Thanks.
Okay, I can control the slides.
Okay, thank you. Let's begin.
Okay, hello everyone. I'm Lan Chengjin from Zhongguancun Laboratory. I'm going to introduce the new intra-domain self solution. Currently, the adopted intra-domain problem statement document summarizes the problems of existing intra-domain self solutions, and the adopted intra-domain architecture document proposes the architecture of intra-domain Savnet, which focuses on self-on customer-facing routers, host-facing routers, and AS border routers. So following the above two documents, this document proposes the source prefix advertisement solution named SPAR-based Savnet. It allows routers to communicate self-specific information through SPAR messages. In this document, we introduce the goal and the protocol-independent design of SPAR-based Savnet, including the content of SPAR message and the process of self-rule generation. How to transmit SPAR messages between routers is not in the scope, but it's recommended that SPAR messages can be transmitted by using existing routing protocols, such as ISIS, OSPF, or BGP. But protocol designs or extensions are not in the scope. We define two new terminologies. They are subnet and edge router. The subnet used in this document is an intra-domain customer network or an intra-domain host network, and the edge router is an intra-domain customer-facing router or a host-facing router. We summarize four types of intra-domain interfaces on which self should be deployed. The first is single homing interface. It is the interface of an edge router that faces to a single homed subnet, such as interface 3 in this figure. The second is complete multi-homing interface. It means if all routers facing a multi-homed subnet are in the local AS, the interfaces facing this subnet are complete multi-homing interfaces, such as interface 1 and interface 2 in this figure. The third is incomplete multi-homing interface. If some routers facing a multi-homed subnet are in other ASs, the interfaces facing this subnet are incomplete multi-homing interfaces, such as interface 4. And the internet interface is the interface of an AS border router that faces to another AS, such as interface 5 and 6. And we determine the validation mode for each of the four types of interface according to the self-table document. Specifically, for single homing interface, SPAR-based Savnet aims to generate a prefix allow list, which contains all source prefixes of the facing single-homed subnet. Similarly, for complete multi-homing interfaces, SPAR-based Savnet generates a prefix allow list containing all source prefixes of the facing multi-homed subnet. But for incomplete multi-homing interface, Spa-based Savnet aims to generate a prefix block list containing source prefixes of intra-domain single-homed subnet and intra-domain complete multi-homed subnet. Because in this case, the edge router may not identify all source prefixes of the facing subnet without communication between other ASs. And for Internet interfaces, SPA-based Savnet aims to generate the same prefix block list as an incomplete multi-homing interface. To generate prefix love list or block list on different interfaces, SPA-based Savnet describes the source prefix advertisement procedure. It includes three main steps. They are SPA message generation, SPA message communication, and self-rule generation. In the first step, edge routers will generate a SPA message containing four types of information. They are source prefix, interface type, subnet tag, and only source flag. The source prefix will contain the source prefix learned through its local routes to the facing subnet, and the interface type should be one of the single home interface, complete multi-home interface, or incomplete multi-home interface. The subnet tag is a unique tag value that identifies the subnet that owns the source prefix. So prefixes belonging to the same subnet must have the same subtag value. And the only source flag is used to indicate whether the source prefix is only used by the subnet. By default, the flag is set, but in some special cases, such as for multi-source prefixes, the flag should be unset. After generating SPA messages, the edge router will send its SPA messages to other routers. It can use existing routing protocols to transmit SPA messages, but protocol designs or extensions are not in this scope. Now I will introduce the process of self-rule generation for each of the four types of interface. For single home interface, the router will generate a prefix allow list by using its own SPA messages. And the prefix allow list should contain source prefixes learned through its local routes to the facing subnet. In this example, router C has a single homing interface, interface 3. So it will generate a SPA message for subnet 2 with prefix P3 in source prefix and has the single homing interface type. So it can directly generate a prefix allow list at interface 3 containing prefix P3 because the interface type is single homing interface. And for complete multi-home interface, the router will generate a prefix allow list by using both its own SPA messages and SPA messages from other routers facing the same subnet. And prefixes with the same subnet tag of the facing subnet will be added into the allow list. In this example, router A and router B connect to subnet 1. So they will generate SPA messages for subnet 1 and send the SPA message to each other. After integrating the SPA messages of router A and router B, they can generate a prefix allow list at interface 1 and 2 containing prefix P1 and P2 because both prefixes has the subnet tag 1. And for incomplete multi-homed interface and internet interface, the router will generate a prefix block list by using SPA messages. and prefixes with single homing interface or complete multi-homing interface type, and only source flag will be added into the block list. For example, in this figure, the prefix P1, P2, P3 in SPA messages have single homing interface and complete multi-homing interface type and only source flag. So router C, router D, and E will generate a prefix block list at the corresponding interface containing the three prefixes. So in summary, SPA-based Savnet addresses the problems raised in the problem statement draft and can meet the design requirements under the intra-domain Savnet architecture. And here shows the convergence consideration, deployment consideration, and security considerations. In the next step, we'd like to improve the preliminary design, so your comments and suggestions are welcome, and collaboration is welcome. Thank you.
Hey, answer one question. So I think for the proposed solution from the viewpoint of the operator, to generate the SPA message, the operator must define the AV interface type and the prefix the attribute of a prefix. So I think this will take this will like more overhead of the manual work. How do we consider this is burden? Okay.
Yeah, and I will introduce some details in the following slot about how to generate the SPA message.
And now there may be some possibility that the interface type will be changed, but it is not the network topology change. So such change will not be advertised automatically within the IGP domain. So I think you should think how to solve the change or update of the interface types.
Yeah, it can be configured manually, but an automatic way is preferred. Sure.
Okay, thank you. So if there is no other question, we will move the next presentation. Okay, you can begin.
Okay, I can control it. Thank you. Okay, now I'm going to introduce an IGP-based method to implement the SPA-based Savnet in an intra-domain network. Here list the related documents. And the intra-domain problem statement summarizes the high operational overhead and inaccurate validation problems of existing SAF solution. And the intra-domain Savnet architecture aims to address the problems of existing intra-domain SAF solutions by introducing the use of SAF-specific information. And the SPA-based Savnet document proposes a protocol-independent solution under this architecture. So this document proposes an IGP-based method to implement SPA-based Savnet. Here is a quick review of SPA-based Savnet. SPA-based Savnet requires edge routers provide self-specific information to other routers through SPA messages. And then edge routers and its border routers can generate prefix allow list or block list. And the self-specific information contains source prefix, interface type, and subnet tag, and only source flag. The source prefix can be automatically learned through the router's local routes to the facing subnet, and the only source flag is set by default. But how to learn the interface type and subnet tag and how to transmit self-specific information are not described in the SPA-based subnet. So these are the focus of this document. First, the interface type can be configured based on the topology, and each subnet is assigned a unique subnet tag value when it first connects to the edge routers. After that, the edge router can automatically match the interface type and subnet tag to source prefixes of the corresponding subnet because both values are bound to the interface. And we can see, different from ACL-based self, we don't need manual configurations when the source prefix of a subnet changes. And only interface type may need to be updated when the topology changes. For example, an interface type may change from a single homing interface to complete multi-homing interface. So it can require less operational overhead than ACL-based self. After generating the self-specific information, the Savnet agent of a single router can provide its self-specific information to other routers by using IGP. In this figure, the sender router should be an edge router, and the receiver router can be either an edge router or an AS border router. When an edge router distributes IP prefix information of its subnet via IGP, it can carry the interface type, subnet tag, and only source flag with the IP prefix information. And currently, we design two approaches to self-specific information communication. The first approach is to use the existing administrative tag sub-TLV to carry interface type, subnet tag, and only source flag. And the second approach is to define a new subnet tag sub-TLV to carry the needed self-specific information. If we choose the first approach, we can use the existing administrative tag sub-TLV of ISIS and OSPF to carry this self-specific information with the IP prefix information. But there is a limitation. Since the administrative tag sub-TLV is not designed for self, so using this tag sub-TLV may conflict with other routing policies that also use administrative tags. To avoid possible conflicts, additional operations may be needed. And if we choose the second approach, we should define a new subnet tag sub-TLV for IGP, for ISIS, OSPF, and OSPF v3. But it can help avoid conflicts with routing policies using existing sub-TLVs and thus facilitate the operation of self. So in the next step, we plan to improve the preliminary design of this IGP-based method, and your comments and suggestions are welcome. Thank you. Any questions?
Hi, Jeff Has. So this question is broader, but your presentation is a good place to start. So you're discussing the mechanisms to just pass along SAV membership, via the IGP. So this is a way of, distributing the information. I don't know that I've found anything in the current architecture documents or discussions about mechanisms like this, and this will also be an issue for inter-domain as well, as to what the trust model is for these announcements. Your mechanism that you're describing here is basically saying, here are my source addresses that you're allowed to use. And in this mechanism, we are trusting that the IGP is, membership in the IGP domain is sufficient to say this is a valid prefix. And in many cases, that may not be true, because once you subvert any router inside of an IGP domain, you can inject anything that is bad. Is there any commentary in the documentation about trust that I have missed?
Yeah, it is correct. We use RTP to transmit this information, including source prefixes of the subnet and corresponding interface type and the subnet tag.
So I would encourage the working group to discuss where this discussion of trust about generating this information should happen, as it is a generic problem for inter-domain and intra-domain. Thank you.
Okay. But it's intra-domain stuff, so should we discuss these things in intra-domain network?
Yeah, if there are no other questions, we will move to next slide. Thanks, Lanzeng.
Okay, thank you.
Hello. Can everyone hear me?
Wait a moment, I will share a slide and pass the control to you.
Okay.
Okay, I think you
Okay.
can control it. Yeah, let's begin.
Okay, thank you. And hello, everyone. My name is Tian Tong from China Unicom. And I will introduce the source address validation enhanced by network controller. Many newly proposed source address validation mechanisms, such as IGP-based and BGP-based Savnet solutions, take a distributed manner to generate sub-rules. Distributed Savnet solutions acquire source prefix information of other subnets with intra-domain networks or inter-domain networks, utilizing BGP or IGP protocols extensions. So all devices are required to support these mechanisms in order to ensure accurate validation. But they face with accuracy and manageability challenges in incremental or partial development scenarios. So this document will propose a network controller-based solution for enhancing subnet capability in intra-domain and inter-domain networks, which supports accurate verification, automated configuration, threat analysis, traceability, and visualization. Okay, let's see the challenges and limitations of distributed subnet in incremental or partial development scenarios. As we all know, the development of new technologies on the network is gradual, especially in our operator networks. So devices are upgraded gradually due to various limitations such as device performance, different versions, and vendors. As we can see in figure, so there are some routers support Savnet while others do not in the AS. As we can see in the figure 1, router 1 is Savnet router, while router 2 is non-Savnet router. They communicate through router 3. Route 2 is unable to generate its own self-specific information or recognize the self-specific information sent by Route 1, and Route 2 can only use fib for self. When it deploys district UIPF, it will cause a proper block, and when it deploys loose UIPF, it will cause a proper permit. And for the Route 1, it can only get the partial prefix of its own subnet to generate subrules, leading to improper block in both Route 1 and 2 due to incomplete information. And in Figure 2, for the intra-domain, ASBI 123 are subnet routers, while the fourth is a non-subnet router, so it can't generate accurate subrouters without obtaining the self-specific information from other routers in its AS and from other AS. So as a result, routers with distributed subnet couldn't generate accurate subrules in incremental or partial development scenario, and furthermore, enhancing the protective effectiveness and incentiveness of subnet is necessary too. Okay, let's see the challenges and limitations with special IP addresses. We can say prefix 1 to 4 are common prefix, where prefix 5 is an anycast one that has multiple legitimate origins. Subnet or law list can be applied on interface A, B, C, and the block list be applied to interface D and E. If router 1 couldn't recognize prefix 5 as prefix anycast prefix, the block list could include the prefix 5. This would result in legitimate packets with prefix 5 being a proper block upon entering through interface D and E. To prevent anycast prefix from being inadvertently added to block list, subnet 1 must advise prefix 5 with a special flag to indicate its anycast later. Distributed subnet solutions have no manually identify and manage special addresses, such as anycast 1. It significantly increases management and configuration burden. So in centralized subnet, the prefix type can be ascertained and configured on the edge router via controller. Wait a minute. Okay. And let's see some other requirements for centralized subnet. The first part is subnet routers need to be configured. Current framework offers optional verification disposal options, including drop, rate limit, or permit the packets. But these disposal strategies should be configured on the subnet routers. And then the subnet tag interface type, only source flag should be configured on the source on the subnet routers based on the topology too. And then verification modes such as a law list and block list should be configured on the corresponding interface. So we need automatic configuration. Centralized network controller can deliver subnet and prefix information, dynamically adjust the authentication modes, disposal strategies for subnet routers by configuration delivery, offering great flexibility in network management. The second part is obtaining information from external system. Centralized controller is more suitable to establish information exchange channel with IPKR client server than the routers themselves. And the third part is analysis and traceability requirements. Distributed subnet doesn't have the capability of the spoofing packets analysis and the threat source tracing. The centralized controller can gather the spoofing packets from subnet routers, enable centralized analysis tracing, modularize the attack source and target, enhance the effectiveness of SAF significantly. Then is to avoid IP addresses and IP prefix conflicts so as to avoid disrupting standard subnet operations. Okay, this section describes the intra-domain and inter-domain self-enhanced solution based on controller. Figure 5 shows the architecture of self capability enhancement system, which consists of infrastructure layer, management and control layer, and application layer. Infrastructure layer is divided into data plane and control plane. Management and control layer refer to a centralized network controller, and the upper application obtain external self-control policies and display and share self-threat information. So the controller can collect all self-related information within AS, generate AS rules, and deliver them to edge, border, or other needed routers. And controller can generate sub-rules based on sub-specific information obtained by the subnet ASBR and send them to the ASBR which don't support the subnet. And the interfaces with external systems to generate more accurate rules. And the controller can support automated configuration, threat analysis, traceability, and visualization, and so on. So until last, let's say the next steps. We will give the scheme design, describe the key technologies, centralized sub-rule generation, and use cases. The first part is the key function module of devices and controller and the interfaces between them. And the second part is focused on the centralized sub-rule generation methods and the steps. And last is the typically use cases. We will give several use cases to illustrate that the centralized subnet can achieve more accurate and comprehensive cell. The first case is intra-domain edge and the border protection. The third is inter-domain protection. And the fourth is more accurate protection with unicast IP addresses. So we will improve the preliminary design and give some impossible implementation and verification. So your comments and suggestions are welcome, and collaboration is also welcome too. That's all. Any comments?
Sex 20, I think the controller-based solution is one useful complement proposal to our overall solutions. But I think we will not depend solely on the controller-based solutions. I think we can discuss such issue later on the list. Okay, thank you for your presentation.
Okay, thank you. And we can discuss later.
Yeah, okay.
Yeah,
Now
and the controller solution, it's an enhanced solution to the subnet.
Yeah, okay.
Yeah.
Yes. Okay, thank you.
Okay.
I think you can consider the proposal by Jeff. He will present later for your overall solutions. Okay.
Hello, everyone. I'm Jeff Haas. I'd like to apologize to the working group that this draft did not come out before Monday. And I would like to thank the chairs for enabling a short presentation of this. This presentation is about a mechanism for distributing source address validation enforcement state in BGP. I'm calling it SAVD. The goals of this mechanism is to deal with the efficient distribution of SAV tables as an abstraction to forwarding elements in the network for SAV enforcement. BGP is the transport protocol that's being proposed here. The thing I would actually request you to do is, I'm talking about BGP, but think about this in terms of this is a way of distributing state and matching state. The protocol mechanism could potentially change. I am calling the mechanism that actually is distributing this a SAV controller. We don't have a SAVD controller. We do not have a specific piece of terminology that I have found in the working group yet about this. A non-goal for this presentation or this mechanism is to talk about how we actually calculate the SAV tables for the devices. As we've seen in prior presentations, there's many discussions about how we gather these things, how we determine the level of trust about the data, and these are going to be a difficult conversation separate from how do we actually program these things. And there are circumstances where a service provider may wish to actually leverage source address validation absent any of these mechanisms, maybe strictly by provisioning. So the operation model that is being proposed in this document is that interfaces and forwarding elements, and I'm using the word forwarding elements separate than routers because the devices that may be doing this stuff could be a switch, a firewall. It may not be anything that normally would speak BGP, but BGP is just the way to shove the data into it. And the data that we're passing is basically the information to provision, what we would generally call a SAV table. The distinction in the document here is this is not a single large table for the entire device. This is really individual sub-tables that are applied to interfaces. And the interfaces get the tables provided by membership. There are 4 classes of membership that's being proposed in here. The first one is that some of the membership might be for a specific interface in the network. There may be a membership that is a subset of interfaces. You could call this a group, an interface set. The terminology will probably evolve as we continue discussions. For most of our intra-domain cases, 2 common memberships will be useful, which is I am having membership based on this is attached to a given peer AS. And again, for the inter-domain case, when you're constructing cones, whether it's a customer cone, provider cone, whatever the set of ASs that are behind you for the set of prefixes are, origin AS is a way to seed this stuff. And we typically think about this in terms of RPKI ROAs or other mechanisms that learned the origin AS information from BGP as an example. I'm going to keep to a relatively simplified topology just for descriptive purposes. This is a very easy presentation. So if we assume some arbitrary BGP topology, we have a pair of routers attached to it, 3 interfaces involved, and there's a controller that is able to install the table. And we have a simplified table here. I'm not talking about enforcement direction. I'm not talking about traffic enforcement. These are things that have very good discussion already across the working group. This is strictly talking about how we get the state around the network. So routers 1 and 2 have interfaces A, B, and C. And the expected SAV table for these prefixes is listed on the right-hand side. An example of an interface-specific membership could be used to populate each of these things. So as an example, prefixes 1, 3, and 4 might be enforced at interface A. Maybe we actually say that, well, interfaces B and C are part of a group that would receive 2 and 5. So the controller actually has been configured to send stuff to this group, and 2 and 5 is what shows up. For pure ASs, we see that we have AS 100 and 200 as adjacent OASs, and perhaps we're telling the controller to distribute things to devices that have tables attached to these ASs for sets of prefixes, say 2 and 5. And our final case, origin ASs, we see this primarily for origin validation. We see this as an example out of like the BARSAV mechanism. We know that this cone of AS is behind here, perhaps at interface A. We know that AS 100, 300, and 400 are in the cone, and we want to actually seed the addresses from whatever the controller says those addresses may be, whether they're constructed by sniffing BGP, pulled in from bar sav, with the augmentations, by provisioning, it doesn't matter. So how do we actually take this set of information and pass it around in BGP? Now, anybody who's familiar with BGP layer 3 VPNs is going to find this a sort of familiar analogy. We're basically creating a new AFI-SAFI, in BGP to pass around SAV enforcement state. The NLRI that's proposed in the document is a very simple thing. It's a route distinguisher and a prefix. Prefixes, for SAV enforcement, may be present in a significant number of forwarding elements across the network. So the consequences, using the groups, we need a way to actually be able to distribute things potentially to a large number of interfaces, groups, et cetera, the various types of memberships we just discussed. And this means that a single BGP packet may not be able to contain all the memberships. And we do actually see this for layer 3 VPNs as well. So the proposal here is that the route distinguisher allows us to actually say this is the originating device, as 4 octets, using a BGP identifier. And we have 2 bytes worth of space to be able to say, these are, this prefix is present more than once, map it in there. Again, we sort of know what these things look like from layer 3 VPNs. And very similar to layer 3 VPNs, how do we actually take this membership and put it inside of a BGP PDU? For layer 3 VPNs, we use extended communities that contain route targets. The SAVD memberships are effectively a flavor of an extended community. And you can see the encodings inside the document. They're not exciting. And you carry for the local membership an IF index, or a group member contains a just arbitrary 6-byte number. The thing that's a little bit special here is that since these things may be a large number of elements for individual device, we're going to use a node target along with these things to scope the locality of this. We'll get into why we actually care about that in a second. For non-scope things, again, it's very boring. It's just a AS number that's embedded inside the community. You already know what this looks like from layer 3 VPNs. The thing that's being proposed here that allows this group style membership to scale out, layer 3 VPNs can happily be deployed, full mesh, IBGP. They can be deployed route reflectors, hierarchies of route reflectors, controllers, etc. But when you're using BGP, especially in a large reflected environment, you need a mechanism that allows for devices to say, I'm only interested in things that are local. A given layer 3 VPN router may have 1 or 2 VPNs attached to it. It doesn't want to see 1,000 VPNs worth of data. A SAV enforcement device may or may not want to see a large or small number of routes depending on what the role is, what it's attached to. And we see this in all the presentations. Once you've calculated the state, it's going to be wildly disjoint as to how things show up. Don't send everything everywhere. The controller needs to know that. The devices themselves only need their local data. RT constrain, RFC4684, does actually have a mechanism to provide, in a sense, a subscription. This device has these local targets, or in this case, SAVD members, that it's interested in. And this will build a BGP distribution graph to send only the things that are of interest. An easy example of this is, say, AS100 has some set of prefixes, and then it adds 10/8. And we need, in the network, to get this to 100 different interfaces. If we're using this type of mechanism, the origin AS is part of the SAVD route. It's thrown in the BGP with the target, and the RT constraint graph pulls it to only the subset of devices that care about it. So very efficient distribution. I've intentionally not talked about in this presentation about the traffic handling actions. This is stuff that overlaps flow spec and has been discussed as an example, the presentation Nan's going to be having momentarily. Fundamentally, we know that for enforcement, we may want to actually leverage forwarding capabilities, sampling, et cetera. The stuff that flow spec has helped us understand as a tool to help with softer SAV enforcement rather than improper blocks and other types of things. FlowSpec has an encoding for these things. The suggestion is, use it when it makes sense. We do also know that from FlowSpec v2 work that the mechanisms in FlowSpec are problematic in some circumstances. This is an initial suggestion. It'll probably be refined as we actually do the work in FlowSpec v2. But speaking of FlowSpec, and this will overlap now in this presentation, why not just use FlowSpec? Well, I have opinions. There are differing opinions here. And again, the key details I ask you to look at is the memberships. But in terms of the other properties that are important about SAV state, membership is the novel piece here, but these things are unfolding elements that may or may not implement the SAV through the device's firewall. It may be using the VRF level mode. It may be using something else. I believe that if we actually stick this in FlowSpec itself, even if we go with some of the more advanced concepts for FlowSpec v2, we're contaminating the firewall concept of FlowSpec in terms of where these things live. This includes, is the order of the FlowSpec rule for SAV enforced at the same mechanisms, the same rule orders, the same place in the forwarding chain that a firewall has versus SAV? Yet maybe yes, maybe no. One of the points that's actually worth talking about as part of SAV enforcement for the working group as the documents advance is, what is the impact on the forwarding chain for SAV enforcement? Because if it happens in different places, you have questions in terms of your implementation architecture. Does the firewall win before SAV? Does SAV win before the firewall? If you're a security operation, maybe that firewall has to win initially because you need to actually hit a security device. Maybe you need the traffic to be captured for DPI and you don't want the thing to be dropped. These are legitimate questions for operators and implementers. And these things are going to be, I
So
think,
Jeff,
a piece of
you
the
have
conversation.
already used up your time.
I'm already done. So the
Jeff,
last
do you want to take questions? We have a line at the microphone.
Sure. The last thing on the right-hand side here is the subscription, for exactly the same thing. I'm done with the presentation. Thank you.
In one of our last reviews of some of the drafts in IDR, a couple of the security people noted that RT constraint is a security hole. How do you deal with that?
This mechanism is currently only proposed for IBGP. This mechanism is only proposed for IBGP right now.
Again, the complaints from the security people were in the IGP as well as GGP. I'm just noting that, that's a, hi, I'll take everything, and a bad actor could do it. So that's just something that has to be nailed down.
Yeah, it's worth discussing. I don't think it's an exciting piece of the discussion. In terms of the distribution state, the trust thing that we were just discussing for distributing, the actual memberships is, I think, far more important.
Hello, Nangang from Huawei Technology. Yeah, actually we have many talks offline, and yeah, it's very nice to propose a new survey to distribute SAV related information separately from other BGP information. And I have a question here. As Chair mentioned at the beginning, we have a SAV table or SAV role YAML model draft in this working group. So, SAV role are relatively static. So can we use YAML model to install these rules instead of BGP?
And that's the motivation for this talk. I am not super invested in how PDUs actually work. I'm looking at the information model about how things go together, and this is sort of a natural way this information model could be in BGP. As you're saying, the SAV table is got some nice discussion. It's more focused as a single large table right now at the moment. This is a form of refactoring the table on a per interface or interface set basis. I don't think it actually changes the underlying abstraction, but it does have some implications on how it's implemented.
Okay, so you are assuming that the BGP maybe SAVD solution is more suitable to very large subtable distribution.
Yes, this is for basically installing the SAV table for enforcement purposes.
Tony P. Juniper. So Jeff, just clarification questions on the overall architecture. So you gather everything on the controller because without having information from all the peers, you will not be able to compute the correct rules, the closure for all the interfaces, right? To distribute them.
Yeah, the controller is the source of truth here.
Okay. Uh, the other question is, this is purely for BGP peering. So what you do with stuff like customer interfaces that don't run BGP or something, how do you suck that stuff in? It's out of scope here?
That's not true. So again, I mentioned that this might be a forwarding element that has nothing to do with normal internet routing. It could be a firewall. BGP is just a protocol here. This could go in through some TCP protocol if we change things around a little bit. Again, the state, the thing is the thing I'm actually invested in here. And I think is interesting, the working group. Other protocols for actually provisioning it can happen. One of the things that I think is a longer, more worthy talk, maybe for the future, is that this is for distributing the state. How the state actually gets installed in the device could vary. It could actually, as Nan has in his presentation, use FlowSpec as a this is going into the firewall layer. If it's going to the VRF, you have an entire table.
I'm not talking about the installation. I'm talking about how you pick up stuff like CPE that is not running anything, and the subnet is showing up there. You expect the controller to pick it up from IGP redistribution, something. You just don't care, but that's within basic.
BGP is just this distribution protocol.
Okay.
And the final related point there is, if you're running a device that's already running, say, BSP38, the device could actually take this firewall intent, the SAV intent, and decide, well, if 90% of your table is already covered, maybe I install 10% firewall entries. That's my implementation. The local device knows, from the intent what they actually can do.
Yeah, okay. I mean, looks all pretty natural with, machinery that we have working at very large scale. So, yeah. Thanks.
Sriram, NIST. So Jeff, there is like need for two-way communications from the controller to the routers and from the routers to the controller, because the routers would get BGP updates from different ASs. In this case, for example, from AS 100, 200.
Yep. Sorry, if that's the thing you took out that you're misunderstanding. For the topology in question, this is the enforcement topology that we're generating state for. The table on the right is the only thing that's actually being conveyed in this protocol.
But in order to compute the table in the controller, it needs to know, for example, if you have feasible path or loose URPF, the controller, the computations, they need to know as an input what are the different updates that are being received at the routers. Not their best path, but all the updates.
Yes, and as I put on slide number 3, a non-goal is how the state is actually gathered. That is a separate matter from the installation of the state. I completely agree this is a necessary thing. Whether or not these mechanisms for gathering the components and disingling the components go into the same AFI-SAFI, I don't have strong opinions about that. I believe they probably will end up being separate. But as an example, bar-SAV could be used to populate this table at the controller, and the controller then signals in the SAV enforcement state.
Okay, we'll talk some more details later.
Okay,
thank you.
Hi, Li Binliu from Zhongguancun Lab. Two questions. The first one is that you seem to characterize the different membership groups according to the potential incoming directions of the prefix. Is it right?
Correct. So it's 4 different types of groups. The intention of the groups is to say that for this logical SAV table attached to some set of interfaces, the controller and the provisioning of the interface subscriptions are what establish what the interface is interested in for enforcement purposes. So this is a coordinated activity.
Okay, thank you. For the second question, does the routers R1 and R2 in their figure belong to the same management area, or do not have the assumption?
Right. So in this case, it is not a highly dynamic mechanism. The subscriptions are to some extent managed, but the memberships themselves could be, and this is one of the reasons why I'm leaving the details unanswered right now. It is possible for this mechanism for the membership to be dynamically discovered from attachment point, potentially to some of Shriram's points. If we happen to know from a local BGP procedure, maybe supplemented by an initial provisioning protocol, that the customer cone is one specific thing, this mechanism potentially can just simply add itself dynamically to the subscriptions for enforcement. Buttersav doesn't talk about how do you track the missing data as an example. This is a mechanism by which that can be done.
Yeah, Jeff, we must take the discuss on the list. Okay,
Yes.
thank you for your presentation.
Thank you for the time.
Hello, good morning, everyone. I'm Nangong from Huawei. Yeah, it's very nice. I requested a 5-minute slot. It's very nice of the chairs that give me 10 minutes. I prepared 2 slides. I will introduce the use case of BGP flow spec. As we know, SAO rule can be considered as a couple of source prefix and valid or invalid interface set. We in the architecture is mentioned that we can use some management tools to facilitate the source address validation to help install our rules. And the BGP spec is a convenient tool to do traffic filtering and controlling. So here I will introduce a use case to use BGP flow spec to help install such rules. And existing flow spec extensions can also be used to improve the efficiency of such installation. Such as interface set, we can group interfaces so that we can reduce the overhead of control plane. Next, please. Okay, here is the use case. Is one of the use cases. Here, let's focus on this figure. We have a controller, and in the local AS, we have 3 routers. And 2 of the routers with blue color have been deployed Savnet mechanisms. And in the orange router, Savnet mechanism is not deployed. We still use the traditional or existing SAO mechanisms. So there may be some accuracy problems as mentioned in the problem statement draft. So in this scenario, we can use the BGP flow spec to help install the SAO rules on the traditional router. I mean the router with the traditional SAO mechanisms. And the source address validation can be enhanced by installing external SAO rules. For example, when we use existing SAO mechanisms, we may not be able to get the complete set of invalid source prefixes. And we can use BGP flow spec to help complete the source prefixes on the router. So then the orange router can do a more accurate source prefixes filtering. Okay, that's the use case. And about how to generate SAO rules, as introduced by Jeff, we can use different mechanisms. And it's not the focus of this SAO rule dissemination method. Okay, that's all. Any questions? Okay, thank you.
Hey, listen, tell me, I will
hello.
share. Yeah, I will share the slide. Too.
Okay, sure.
Okay, and pass the control to you.
Okay. Okay, I'm going to present the signed Savnet peer information object for deploying inter-domain Savnet. I'm Li Chen from Zhongguancun Laboratory. So how do we turn the page? I don't seem to be able to turn the page now.
Yeah, I will pass control. Okay. Oh, sorry.
Okay.
Huh? You can. So I will transfer.
Okay.
Yeah.
So yeah, let me introduce the background. So SysV is an object that proposes a public RPKI registry that contains all the ASs that both want to deploy Savnet and are willing to set up Savnet peering relationships. So we hope that newly adopting AS can use this registry as a reference and pick the appropriate ASs to set up a peering relationship to exchange specific information. And because RPKI is already a global infrastructure for routing security, we believe that this is the most suitable choice. So the SysV object is necessary for automatic peering. On the right, here's an example, and and for AS4 and AS1 to generate the accurate sub block lists or allow lists, they need to set up connections with other Savnet agents, and using the SysV object, it can identify the appropriate ASs to set up the peering relationships to exchange the necessary information to set up all the lists. So this is the second time we have presented this draft, and in the last Ietf meeting, we have received some comments on our first iteration of the draft. The first comment is on the SysV object identifier, which we should add as suggested after it, because we have not actually been allocated this code point. And the second comment is on the SysV content. And we were asked to extend the object to cover both IPv4 and v6 address families. And we also we also would like to extend the object from only one address to a list of addresses, because an AS can have many Savnet agents. And lastly, we have some comments on the peering establishment algorithms using SysV. We are asked to illustrate the exact algorithms and also want to show the appropriate amount of information needed for newly adopting AS. And finally, we want to make sure that the ASPA is not bidirectional in our current text. So based on the comments, we made some modifications to our current draft. Here are the main updates. First, we revised the content types section to include the suggested and we are going through the process trying to register this code point. And secondly, we revised the SysV content section so that the AS.1 module can cover both IPv4 and v6 address families, and also a list of IP addresses for an AS. And thirdly, we revised the session 6, which is using SysV, with some considerations for establishing peering relationships using SysV, as well as detailed procedures for establishing such a relationship. And lastly, we add a new session called the newly Savnet adopting AS session to specify what a new AS to Savnet can do. And for the, let me go into the details of our modifications to the object e-content. The object is formally defined by the AS1.1 module. The ASID field will contain the AS number that has deployed Savnet and can perform SAV in the data plane. The addresses field contain a sequence of IP family addresses, which store the router's IP addresses within the AS whose ID is ASID. The IP address family field contains the instance of IP family and the instance of IP addresses. The IP family contains a octet to signify whether it's IPv4 or v6, and the IP address field contains a sequence of IP address instances, and each instance is length bounded by the address family. So we also include a peering relationship setup procedures based on the BGP announcement, the ASPA objects, the CISP, and the AS can find the candidate ASs to set up the subnet peering relationships according to the following procedure. The procedure contains 4 steps. The first step is to identify all the ASs in the preferred AS passes to various destinations and rank them in the frequency according to their frequency in a descending order. The next step is that we retrieve the CISP objects and obtain all the candidate ASs and these ASs which have deployed subnet. And the third step is that we want to select the peering candidates based on their rankings, based on all the candidate AS we found in step 2, and we set up a maximum number of candidates, which is based on the capability of the router or the server that is running this half agent. The last step is basically set up the peering relationship with the subnet agents. Next step, please. We also include a new session called the newly adopting ASs, which we have specified 2 operations that we recommend the newly adopting AS to take. The first step is to register a CISP object, and the second step is the second operation that it needs to take is to establishing a subnet peering relationship. And you can refer to our draft for more details on these 2 steps. And yeah.
Okay, thank you.
Thank you.
We have no time for the questions, so we can discuss later on the list.
Okay. Okay, thank you.
Thank you.
Hello everyone. Our topic is Intra-domain Savnet OAM. I will speed up my presentation.
Yeah, I think you can control. Yeah.
This draft focuses on the charter for Savnet working group, the definition of routing protocol independent operation and management mechanism to operate and manage self-related configuration, the implementation of OAM for intra-domain Savnet includes the following perspective. Fault detection, real-time monitoring, use protocols like SNMP, NetFlows, SFlow, etc. Log analysis, performs monitoring, and secondly, the fault detection by alert system. We can cite threshold alerts, and the pattern recognition can be by using machine learning or other technologies. Fault detection by automated diagnosed tool. We can use self-check tools to perform regular checks on Savnet configurations to detect configuration errors. We have a use case for fault detection by PIN. We can use PIN tool to test the correctness of Savnet functionalities. The source host generates a standard SAMP echo request packet and receives a reply. If the local Savnet check false, an error message should be sent to the source and indicating the reason for the failure. And after receiving the reply, the source declares a successful or a failure result. Fault isolation at interface level. If the fault comes to a specific network, you can temporarily disable the data interface to prevent the spread of the abnormal traffic. And we can modify the routing policy to reroute traffic around the faulty interface at the level, we can adjust a routing table to avoid traffic through the faulty node path, and we can withdraw route advertisement for the faulty path in BGP. At a device level, we isolate faulty device, and if the fault is a temporary issue, we can restart device to restore it. Configuration, it concludes base configuration like a global enabled or disabled capacity such as max cell entry number, the mode such as interface-based prefix, alloy list, block list, or the other mode, and action for unknown source prefix. And we have similar interface configuration, and we can also have static self entry, and we for the protocol configuration, we have the IGP self enabled in IPv4 or IPv6 in both disabled and the self interface enabled, and BGP self enabled. Notification faults detected by proactive mechanisms, and the reception of event-driven defect indications, logged security incidents pertaining to the OEM message channel, and protocol errors may be caused by misconfiguration. Accounting routers may the following statistical functionalities are required. Global statistics, including the number of the packets passed, drops, lookups not found, and the blacklist hit, and the interface-based statistics, for the permit list hits, block list hits, and the lookups not found, and the statistics for this card traffic sent from internal to external, and sent from external to internal, and we also account the per Savnet table entry statistics. Performance management allows for the management of packet forwarding, performance transmission performance with a domain, including latency and packet loss, which can be used for network fault analysis. A tool like Savnet pin can be used for simple performance testing to initially locate the network fault. Thank you.
Okay, thank you. If I think you can begin. Okay.
Hello, can you hear me?
Yeah, okay, we can hear you.
Okay. Hello, everybody. My name is Ruifeng Li, and I'm from Zhongguancun Lab. Today I'll talk about mirroring soft deployment with Soft-T, and I will be very quick because the time's up. So first, what is Soft-T? Soft-T is a platform for testing and disclosing deployment data of source address validation. For testing, Soft-T client is easy to install and runs on one click. For disclosing, Soft-T collects users' testing data for research use only and discloses data with users' permission. Soft-T can test many different dimensions of source address validation, like private addresses, routable addresses, and it can test the direction of source address validation, like that is the inbound and the outbound. Soft-T can also test IPv4 addresses and IPv6 addresses, and Soft-T can test the spoofable prefix length. And this is how does Safety work. And we mainly do 4 tests. That is outbound spoofing test, inbound spoofing test, traceroute test, and trace filter test. And there are some details of how does Safety work. And I think I skipped this section. And this is how does Safety disclose measurement results. And first of all, Safety will only disclose outbound source address validation data on user's permission. And in the pictures is an example of our disclosure. In the first section, the first section is a summary section, and we will disclose the most important information we tested in this session. And for example, on the routable row, we have an IPv6 received label, and it means packets with spoofed routable IPv6 address will not be blocked. And we will also have some more detailed information in each test session. So what's next for Safety? The first, we are still working on trace filter. And the second, we are trying to figure out how to promote Safety. We are seeking cooperations with universities, and we are working on distributing the measurement tasks on crowdsourcing platforms like mTurk. And we are also trying to contact network operators via emails. And that's all of my presentation. Thanks for your listening.
Yeah, thanks, Rachel. We would like to see some test result in the coming meeting. Okay, thank you.
Okay.
Thank you all of the participants, and see you later in the next meeting. Okay, thank you.